Good day, this is Jim Pytel from Columbia Gorge Community College. This is Digital Electronics 1. This lecture is entitled Combinational Logic Design Using Karnaugh Maps. I could just as easily call it Developing Truth Tables, then taking that truth table and developing the minimum SOP expression from that truth table using stuff you already know. This is a lecture where we learn how we lure that bear into the trap. What are we going to do? We're going to give him some honey. I don't know what that bear is eating. It looks like a pork chop. If it really is a pork chop, I'm going to wrestle him because I love pork chops. But what we're going to try to do is learn how to just take real world expressions, like someone says something to you or you want a machine to do something, and based off those inputs, what does the output look like? What we're going to do is we are going to use some silly examples that will hopefully be memorable. And what do bears eat? What we're going to do is we're going to do, what does robot bears eat? Robot bears eat zeros or ones. And there's the three bear brothers, A, B, and C. So A, B, and C, they're brothers and they want to go ahead and go out to lunch and they want to decide what to eat for lunch. And everyone's got to vote. They can vote for eating zeros for lunch or eating ones for lunch. And what they can do is they're going to try to do this very democratically. Majority vote. What I'm saying is if two of them vote to eat ones, they eat ones. If two of them vote to eat zeros, they eat zeros. If all three of them vote to eat ones, what do you think they're going to eat? Zeros? No, they're going to eat ones. So what I'm saying is take that expression that I've given you. It's a majority vote circuit. They have two choices, 0 or 1. What's the output? What's lunch given those inputs? Every bear has a vote. Step 2. That's step 1, is just set up the truth table. Step 2, populate the truth table with all possible combinations of input. What are all possible combinations inputs for the three brothers, A, B, C? Well, it's 000 to 111. Fill it out. There you go. If you missed a combination, 3 zeros stands for 0. 001 stands for binary 1, 2, 3. Just think of that. Use the binary equivalents of those. Use those as a check to do that. Again, it's every other, every two, every 4. If you can't do that by now, guys, I don't know what to say. You're going to mess this up. You are going to mess this up if you do not have the ability to generate all possible combinations of input to a truth table. If you don't have that ability, you're going to skip something. Let's say I skipped 5. You don't know what that output is. You're not going to be able to put your K-map in there. So that was kind of step 2, is generate all possible combinations of input. Step 3, think about it. All 3 bear brothers want to eat zeros for lunch. What are they going to eat? They're going to eat zeros. So what I'm saying is go through the truth table. Based upon those inputs, what is the output? It's a majority vote circuit. Looks like A wants to, and know what I'm talking about, I'm here now. A wants to eat a 0. B wants to eat a 0. The majority says they want to eat 0. Tough luck, C. We're all eating zeros. Look at 2. Case 2. A wants to eat a 0. B wants to eat a 1. Too bad. Who's the tiebreaker? C is a 0. Okay, so what do they eat? 0. All right, go through. Fill out the truth table. Step 3, think about it. And that is honestly one of those things I can't teach you. You just got to take every single combination of input, and based on those circumstances, it is not going to be the same. Every single circuit you get, it's going to behave differently. Okay, so for this majority circuit, your final output, pause the lecture, go ahead and see if you can figure this out, should look something like this. There you go. So it looks like we've got 00010, 111 going in that direction. What do I do now? What's the minimum expression? Again, because these are robot bears, they're going to do a very democratic, they've set up their truth table for a majority circuit, and what they're going to do is they're design their logic circuit, and each bear has an opportunity to register their vote, and it's going to come out what they want to do. Again, being super smart robot bears, they want to go ahead and have a minimized SOP expression. So take the truth table, put it in a K-map. Take the K-map, do the K-map analysis, come up with a minimum SOP expression. All right, so here's my blank K-map. Okay, there's my blank K-map, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. How am I going to order it? C, B, A? Don't think so. Make your life easy. A, B, C. order in the way the truth table is. By the way, what's this? I sometimes put these things down here at the bottom because sometimes we will be having, here's my ins, some of these later examples, we will have one or more outs. Okay, so that is my first K-map for my, in this particular case, it's my one and only output. Just keep yourself organized. Put it in the K-map. I'm looking for ones. Where are the ones? Well, there's one at 0, 1, 1. There. I'm looking for a 101. There. 110. There. And finally, there. Go ahead and group it. Once you've got the groups, go ahead and see if you can come up with a minimized SOP expression. And this is the kind of the step here that some people forget about. The answer you get should make sense. Does it make sense with this expression given the statement of logic here that says, okay, I want a majority vote circuit where A and B and C get one vote each and their vote counts once. Who gets the majority? Your answer should make sense. Let's try a grouping. There's a group of 2. Group of 3? Nope. Group of 2 with another group of 2. What are the terms for the red, the blue, the green? Or them together. So lunch, the expression lunch equals red. It looks like A and B. What is the expression for the blue? It looks like B and C. Or the green looks like A and C. Does that make sense? Think about this. A and B have to agree. They've got a majority. Or B and C have to agree. They've got a majority. Or A and C have to agree. They've got a majority. Anytime any two brothers agree, they get to eat what that majority has decided. So this is a really neat, simple example of how you use a statement, a desired output, put it into a truth table, and then once you've got that truth table, go ahead and execute it with a K-map. All right, so let's try a follow-on example of the 3 robots here, and let's try this. Okay, very similar, stupid example. A, B, and C want to decide what they want to eat for lunch. The robots, what are their choices? They get a choice of 0 or 1. They all get 1 vote. But Robot Dad is coming along. Robot Dad carries a lot more weight than the kids A, B, and C. He gets 2 votes. Go ahead and see how this truth table results. And I might give you some further guidance with this, which may or may not be necessary. In the event of a tie, Dad wins. Okay, in the event of a tie, the side with Dad wins. All right, so this is not as easy as our last majority vote circuit. And what I'm telling you is you only need 4 variables. Okay, you only need 4 variables. I know A gets 1 vote, B gets 1 vote, and C gets 1 vote. You might be tempted to do D1 and D2. No, 4 variables. And it's tricky. All you got to do is think about it. Think about it. Take A, B, C, and D. Make a bare truth table. Okay, so let's make a bare truth table. There you go. What's our possible inputs? Well, A could have a vote, B could have a vote, C could have a vote, and D could have a vote. There's lunch 2. Because we already did lunch 1. Think about every single possible combination of inputs. Do you know why I only do 4 variables and not 5 variables? Because then you'd have to think about 32. 6 variables, you'd have to think about 64. Yeah, I want this thing done within a half hour, whatever. Just think about it. Every single possible combination. Think about the first one. Everybody wants to eat zeros. What do they eat? Zeros. Everybody, including Dad, well, most everybody, including Dad, want to eat zeros. A wants to eat a 1 just because he's a jerk. Too bad, A, we're all eating zeros. Too bad, B. Okay, here's a neat thing. Here, what's going on here? D gets 2 votes. So there's 0, 0. C gets 1 vote, 0. The ones. B gets 1 vote, A gets 1 vote. Who wins? The majority wins. 0. Okay, so what I'm saying is think about it. Think about every possible combination. Go through and see if you come up with a truth table that may or may not look like this. I did fill out the full truth table because I wanted to show you just a little simple mnemonic device, just a little potentially that may simplify what I'm asking here is just think about it. Is what are the number of votes? You got 3, A, B, and C, and then D counts for 2. So there are 5 possible inputs to this thing here. And just how are they apportioned between zeros and ones? In this particular circumstance here is D wants a 0. So there are 2 votes for zeros, and then add B's to it. So there's 3 votes for zeros. And now add C's vote for a 1 and A's vote for 1. So you got 2 votes for 1. What are they going to get? 0, 0. Here's a neat circumstance right here. These two right here, which I've designed, which I've kind of highlighted. D wants a 0, so there are 2 votes for 0. A, B, and C want 1s. They've outvoted Dad. That's the first time we get a 1 there. Just because he doesn't want to be a jerk, he's going to say, okay, all 3 of us, everybody's going to go ahead. We're going to eat a 1 because you 3 have agreed. Similar circumstance to what's going on here. We've got 2 votes for 1, but we've got 3 votes for 0. 0. Okay. So again, if you had troubles before, see if you can use kind of this interpretation of it. And you are authorized to do this thing. You are authorized to go ahead, put interpretations of this, and even describe, even write it out. Here's those circumstances: is kids A, B, and C outvote Dad, which is D. Having these little reminders to yourself and somehow these interpretations here will help you develop these truth tables. Let's go ahead and I'm going to fill out the rest of this here and see what we get. Okay, there you go. There's my truth table. And I don't know if you noticed there, I had flip-flopped the votes and the interpretation. So again, my interpretation may have been wrong, and as a result, my truth table. So go ahead, let's check our work. Okay, and that's looking good for our truth table. And one of the things too is just look at your truth table before you go through all this KMAP, before you come up with your minimized SOP expression. You should already see something in the truth table that's going to remind you of how your minimized SOP expression is looking like. I mean, just look at what's going on. Anytime D can get either A, B, or C, any one of those guys, he's going to get his way. Why? Because he's tipped the scales in his favor, 3-2. Okay, or 2-3 as the case might be. When does D get outvoted? When A, B, and C agree. Think about that when we put it into a KMAP and develop the minimized SOP expression. KMAP it. Okay, I know A goes before B, C, and D in alphabetical order. I know you want to do A, B, C, D. Don't do it. Your truth table's set up to do D, C, B, A. You can just read it off. Where are those 1s? Make it pretty. Put the 1s in there. What you're going to come up with is something like this. There you go. What's the next step? We put this thing inside the KMAP. Is just go ahead and group the thing. And this is pretty challenging. Okay, if you really understand how groups work, you're going to have no problem doing this. All right, and I'm going to do the actually, you know what? Go ahead, come up with the groups. And then you've got don't worry about the final SOP expression here. Go ahead and pause it, come up with the groups. You should come up with 4 groups. Okay, hopefully you've paused it, and now we're going to go ahead and try this. I'm going to grab a group of 4. I'm going to grab an overlapping group of 4. I'm not going to grab a group of 6 because that thing doesn't work. It doesn't work that way. And some of you might say, well, let's do the easiest one, easiest identifiable. There's no such thing as a group of 3, so I'm going to grab this group of 2 with a little overlap. You may have been tempted to do this. That's a group of 2, right? Wrong. Maximize the size of the groups. Okay, how do I maximize the size of the groups? Think about this. 1s, 2s, 4s. 4s don't always come in squares. They're also in lines, ups and downs, lefts and rights. Okay, so there's the groups. What are the expressions for the red, blue, pink, and green product terms? Once we've got those expressions, we should be able to come up with a minimum SOP expression. And again, what's the last step? It should make sense. It should make sense, just what we described. Anytime the dad gets one of the kids to agree with him, he gets his way. And anytime the kids all agree simultaneously, A, B, and C, they can outvote dad. Okay, let's go ahead and come up with okay, pause it, and hopefully you've come up with the following product term. So red. Red to me looks like D. Makes sense because D's got some weight there, and it looks like B. So basically, when dad and B agree, or term in the blue, what you think matters? D and A. Okay, so anytime dad and A agree. Finally, not finally, but next, D, the one in the pink, and C, because they're all in that same row. Finally, the last is this group of 2. It looks like C and B and A. This makes sense. The kids will get their way if all 3 of them simultaneously vote the same way. When dad and B agree, it should make sense. Dad and A agree. Finally, when dad and C agree. The expression for lunch 2 is equal to D and B, or D and A, or D and C, or C and B and A. So hopefully this is a pretty good idea of what you're going to be doing in these circumstances here is taking your truth table, all possible combinations of inputs, and you cannot forget one because you're going to mess up the whole thing. Let's say you got 14 inputs. Well, you're going to miss 2 of them, and you can't populate your K-map correctly. So all possible combinations of inputs, think about it. Derive your output. What does the output behave for every single possible combinations of inputs? Use these extra columns. Remind yourself what's going on. Take that truth table, trouble check it, put it in the K-map. Take the K-map, generate the product terms for the groups. Take those groups, put them in a minimum SOP expression. Bang, there you go. D, C, B, and A go ahead and execute this minimum SOP expression, and they vote what they're going to have for lunch. So beyond these 2 examples here, let's go ahead and put some more practical examples, something that we might run across in our labs or some of the circuits later on this year. Okay, so for example 3 for combinational logic design using Karnaugh maps, we're going to go into a detailed analysis of one of those common functions of combinational logic. Namely, in this particular example, it's a decoder. You've reached a significant milestone in your digital electronics education. We can start developing really cool functional circuits. And a decoder, kind of like one of those definitions that's like nailing jello to a tree, because there are a bunch of different types of decoders out there, and the easiest definition, the most general definition for a decoder I've ever found is the following. Basically, a decoder detects the presence of a specific combination of bits, i.e. the code, placed on its inputs, and then it indicates that presence with a specified output level. Specified could be 0 if it's syncing or 1 if it's not. Basically, it's going to say, hey, I see this, hey, I see that, and it's just telling you, hey, here's a code. And this is not example 3, by the way. Here's the world's simplest decoder. I want to detect the presence of the number 10, decimal 10, and I've got 4 inputs. I've got 4 binary inputs, A3, A2, A1, A0, and they can take binary values, 0 or 1, where this is the MSB, A3, and that is the LSB, the world's simplest decoder. I want to be alerted when decimal 10 shows up. Here you go. Just feed 10 to an AND gate. That when I get the combination 1, 0, 1, 0, i.e. the binary representation of decimal 10, it lights up or doesn't light up. How am I going to do this? Invert that LSB, invert that. Oh, don't do anything with the MSB because here's my AND gate, 1. Well, that was a 0, it's a 1. 1, that was a 0, it's a 1. What is this AND gate? 4 1s. And if it's a sourcing relationship, my LED lights up anytime I get 1, 0, 1, 0 on my inputs. Want a syncing relationship? Too easy. Make it a NAND gate. Current controlling resistor. There's my LED. Test it out for other combinations. Does the world's simplest decoder light up for anything other than 10? Doesn't, for all possible combinations of input right there. But I digress. Okay, so let's make a decoder. All right, and this example, we're going to use, I want to detect the presence of all the prime numbers in our 4-bit inputs. And I know one's not really a prime. If you don't know what primes are, I'm just going to make a list for you. I know 1's not really a prime. I think it is. I think it should be. So what I'm going to do is I'm going to detect the presence of 1, 2, 3, 4 is not prime, 5, 7, 11, and 13 within our 4-bit combinations. That's the most I can detect up to. If I wanted to go further, I'd have to add more bits to it. Okay, and I know that's not really prime. Read about prime numbers. They're awesome. Some of my favorite numbers ever. Very cool, very, very neat things you can do with primes. I want to indicate the presence of those prime numbers, including my honorary prime 1, with a 1 as the output. Develop the truth table. Develop the minimum SOP expression that will implement that. So I'm going to pause this and pull up a bare truth table, and let's call that, again, A3, A2, A1, A0 are our inputs. Okay, there you go. There's our bare truth table. I'm going to call this my MSB A3, A2, A1, A0. I'm going to call this output prime. Is 0 prime? No, actually I don't think it is. I don't know. Is 1 a prime? Not really, but I'm going to say it is. Is 2 a prime? Yes, it is. Just fill out the truth table. What I'm saying is go think about it. Is 3 a prime? Yes. Is 5 a prime? Yes. 7, yes. And fill all these things out. 11, 13. What do the rest get? Zeros. What's the next step? Put it in a K-map. Make a bare K-map. There's my K-map. Notice I'm staying the same order that my truth table is. Fill out the K-map. Just map that truth table into this K-map. You should get something like this. There you go. I've got 1, 3, 2, 5, 7, 11, and 13 all accounted for. So what you're going to do with this perfect K-map, you're going to group it. Go for the biggest group first. There you go. There's a big old group of 4. Group of 3, nope. Group of 2, another group of 2. Group of 1, incorrect. We are wrapping around adjacency, another group of 2. You've got the truth table, got the K-map, group the K-map. What do for the expression prime? Come up with the expression, the product expressions for each one of those groups, summate them together. So what is, set ourselves up here, prime, I should say the word prime-ish, not to be confused with primus, because one's not really prime. I know some mathematical sticklers out there might be freaking out, but I'm going to still call it prime. Is red, ORed with blue, ORed with pink, ORed with green, should come up with my final minimum SOP expression. All right, so go ahead and try it. And I'm going to come up with the following. So for the first group of 4, it should be not A3 ANDed with A0, excuse me. Let's go ahead and try for the blue. What I'm getting for the blue product term is not A3 ANDed with not A2 ANDed with A1. Okay, let's go ahead and try for the green term. Okay, the green product term is A2 ANDed with not A1 ANDed with A0. Go ahead and try for the pink term, and the result for that one should be not A2 ANDed with A1 ANDed with A0. It helps to be super organized with these things, especially when you've got it written in that MSB2 LSB format, because it'd be super simple to confuse an A3 with an A2 or vice versa. Okay, so go ahead and check our work. And there you go. So that is looking good for a prime number detector for the numbers 0 through 15. And basically anytime we could have a counter as those inputs, and it's going to count from, where is it going to count from? It's going to count from up. It's going to go from quadruple 0 to quadruple 1. And every single time you get a 1, it blinks that LED, blinks that LED, blinks that LED. No, blink, no, blink. No, 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 blink, no, blink. It's a prime number detector. It's telling you, hey, I see a prime number. Hey, I see a prime number. Hey, I don't see a prime number. Again, that was for a sourcing relationship. Syncing, make a NAND gate. How would I do this here too? How would I do this just using NAND gates? And you should already know the answer. What do NAND gates, feeding NAND gates make? It makes an SOP. This is the easiest thing about this. How many product terms do I have? I have 4 product terms. Make them all NAND gates, feeding a NAND gate. What does this mean? And I know I'm not, so A3, here I'll draw a pretty representation of this. So here's a kind of pretty representation of this using one-line notation. What's the first NAND gate get? Well, it gets not A3. How do I generate not A3 from A3? Take a NAND gate, put its inputs together. What do I get is not A3. That's how that inversion is generated. And hook it up with A0. The second NAND gate, also not A3, not A2, A1. The third NAND gate is A2, not A1, A0. The fourth NAND gate is not A2, A1, A0. It's the simplest representation you can possibly come up with using an SOP expression. How do we do it? We thought about it. We just took our logical expression, build me a prime detector plus 1. I want a high output when I see a prime, put it in a truth table, put it in a K-map, came up with a minimum SOP expression. And what we did was just a quick implementation of it using just NAND gates, understanding that the inverse or the complements are also being generated with these NAND-based inverters. You want another example like this? I don't care if you want another example or not. I'm going to do another example. These number things are awesome. There's limitless combinations that we can do with this. I'm just going to leave you as an example. We'll just try this one. That was example 3. So let's say example 4. I'm going to leave you to do this by yourself. I want you to design a decoder that detects the numbers 2 through 6 inclusive. So 2, 3, 4, 5, and 6. That's what I say, 2 to 6 inclusive. Make a 2 to 6 detector inclusive, and I want a high output when it sees those. And we'll come back to visit that thing again in the Unit 5 review. So hopefully you come up with the same answer. Another kind of limitless source of example problems is something we've already kind of discussed already. It's another kind of decoder. It's the 7-segment display. The 7447 BCD to 7-segment display driver. It's a decoder. Like I said, decoders are hard to define under a general definition, but it kind of fits that really broad definition. What is it? It's What's a decoder do? It detects the presence of a certain combination of inputs. What's the BCD to 7-segment decoder doing? It's putting BCD numbers on its inputs. What's it doing for the outputs? Well, it's driving the A through G segments of a common anode 7-segment display. It's a decoder. It's recognized the presence of, let's say, 0001, the number 1, and it's outputting appropriate signals to drive A through G segments to display the number 1. So let's use that as example. Since we skipped the answer for example 4, I'm making you do that by yourself. Let's call this example 5. Okay, one thing before we do these problems here is how does the 7-segment display look when it's displaying these numbers? Just write it out. When it goes 0 to 9, can it display anything beyond 9? No, it can't. So you got to know how these things work. Okay, you should come up with something very similar to this. Okay, so there is what I think a 7-segment display looks like when it's displaying a 0, which segments are lit up: A, B, C, D, E, and F. When I'm displaying a 1, B, and C, 2, A, B, D, E, and G, so on and so forth. This is the one that always kills me, 6. Is there a bar over? I don't think there is. For the intents and purposes of this exercise, let's just say there's no bar. By the way, what are the segments' names? 7-segment display, there's 7 of them. There's A, B, C, D, E, F, G. It's driving a common anode. So everybody's got a positive connection. Everybody's got a positive connection. It's a common anode. To get it to light up, I've got to provide a 0 to those segments that I want to light up. So for the number 0, which segments do I want to give a 0? Obviously, A, B, C, D, E, and F should have zeros. It helps to have an understanding how the thing works to begin with. And what I'm going to do, this is not the full-blown 7447 BCD to 7-segment display driver. This is not the internal logic. What I'm doing is an incredibly simplified version of it. All I'm looking for is the A through G segments. I know there's lamp tests and blanking indicators. Don't worry about those right now. All I'm saying is let's worry about A through G. We're going to come up with a simplified representation of this. What I want to know is, what is the display logic? What is the SOP, the minimum SOP expression for each segment? What I'm saying is given the inputs quadruple 0 to, again, there's 4 possible combinations, up to quadruple 1, how can it display these numbers? Okay, and there's a problem there. Because BCD, it goes from 0 to 9, i.e. quadruple 0 to 101. What happens at 10? What happens from 10 to 15? It's invalid data. It's invalid data. So what we are going to assume is, for the intents and purposes of this exercise, numbers 10 through 15, decimal equivalents 10 through 15, have been excluded, and we will never see those inputs. So let's make a truth table, and I want you to put 0 through 15 there, and I'm going to show you a neat trick. It's called the don't care. Okay, so I'm going to go ahead and make a bare truth table, and let's call this DCBA, because I don't want to get lost with those MSB numbers. It's called DCBA. So there is my truth table, DCBA. There's my little cheat sheet above, what those things look like. And another cheat sheet, that's A, B, C, D, E, F, and G. One another cheat sheet, it's common anode. It means 0 to light. So we're combining a bunch of things in this one simple example problem here. And I'm going to introduce something totally radical. It's called the don't care. I told you that you will never get numbers from here to there. What I'm going to put is what this thing is called a don't care. It's an X. We'll come back to it later. You will never get those numbers. So it means you don't care. You never have to worry about those things. Okay, what are the outputs that we want to develop? What are the outputs for a 7447 BCD to 7-segment display? Well, it's the inputs. It's BCD numbers coming in the form of DCB. This being the D being the MSB. What are the outputs? Well, it's a bunch of outputs. It's A is an output, B is an output, C is an output, all the way down to G. So basically, we're going to have to develop 7 outputs. We're not going to do that for this example. I'm going to leave a couple of them to you. Let's develop the output for segment A. So just think about it. It takes a 0 to light. It's active low. Which numbers does it need to light up at? Well, it needs to light up at 0. It needs to light up at 2, 3, 5. That's what I'm saying, is put those combinations there. 1, 2, 3, 5, 6, 7, 8, 9, obviously 10, 11, 12, 13, 14, 15 don't matter because they don't care. We'll come back to it, how we use those in a second here. Which ones again? Again, which segment are we looking at? We're looking at A. It's a 0 to light up. Okay, I see it lit there, 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 and there. So it looks like 0 is going to have a 0 because it's taking a 0 to light up. 2 is going to have a 0. 3 is going to have a 0. 5 has a 0 on it. 7 has a 0 on it. 8 has a 0 on it. 9 has a 0 on it. If I don't want it to light up, what am I going to put on it? A 1. 1, 1. SOP expression. We're looking for the ones. Okay, I know we had an active low to light, but I want to come up with the SOP expression for segment A. For segment A alone. We're not worrying about B, C, D, E, F, and G right now. We'll come back to those later. You may come back to them later for example problems. It's a quasi-limitless. Actually, it's not limitless. You got 7 opportunities for example problems here. Put it in a K-map. And what I'm going to say is put those don't cares in there. And I'm going to show you something totally cool. Here's my K-map. D, C, B, A, 0, 0, 0, 1, 1, 1, 1, 0. Same thing. Take the K-map. Take the truth table, put it in the K-map. It should look something like this. Put those don't cares in there too. Okay, so where are the ones? It's in 1. It's in 4. It's in 6. Where are the don't cares? It's 10, 11, 12, 13, 14, and 15. And I know I said put the don't cares in there. Here's an example what that K-map would look like without the don't cares. 1, 4, 6. This is neat. A don't care. If you really, truly don't care, if you will never get the values 10 and 15, there's some other exclusion device beforehand that makes sure that you will never get those BCD numbers. It means you're never going to get those possible combinations of inputs. So it doesn't matter what the output is. It could be a 0 or a 1. I could put a 0 or a 1 here, but I'm just going to put an X. And this implementation, which I've drawn on the right-hand side here, is as if those don't care situations are read as a 0, okay? So if I ever accidentally got the combination 1, 1, 0, 0, that segment A would light up, but I don't care. I'm never, ever going to get the combination 1, 1, 0, 0 because it's 12 and it's not BCD. Don't cares. Use them as ones if they help you. Don't use them if they don't help you. Okay, so let's look at our K-maps and see if we can find groups. Let's take a small one that you should easily be able to do. That guy right there. It doesn't have any don't cares in it. Is there any other cells that are adjacent to it that I could potentially include in that group? No, I can't. Okay, so for that red product term right there, it's D, C, B, A. It's not D, not C, not B, and A. The other group, can I use the don't cares to help me? If they help me, use them. If they don't, don't. I'm going to try to use it as if they weren't there. I might grab that group and that group. That's wrong too. That's wrong even without those don't cares, because via wraparound adjacency, that one is adjacent to that one. But that's still wrong. Use them if they help you. Don't use them if they don't, because check this out. What if I could grab that and that into a single large group of 4? And I compare and contrast to what we get here not using the don't cares. Red guy's still the same, can't do much there. What is the term is in blue? What I'm getting there is C and not A. What am I getting here for this term in blue? It's not D and C, and it looks like not A. Use them if they help you. Did they help me? Sure did. Look at that. It's a smaller product term. It's got C and not A. Look at this guy's product term. Not D and C and not A. I'm adding an unnecessary term there because I'm using those don't cares to help me, and I'm not using them if it doesn't. Okay, so my total SOP expression, segment A, is equal to not D and not C and not B and A, or C and not A. Okay, and I'm using those don't cares to help me. Again, limitless, quasi-limitless possibilities. Find it for B, C, D, E, F, and G. Just because I like these things, let's go ahead and do B's logic here. So all of these guys are excluded. When does segment B light up? I'm going to go ahead and clean up our little 7-segment displays here. Clean this thing up. I've added another output column, and this is what I'm saying about staying organized here is we're going to have 7 outputs, A through G here. So you're going to have 4 inputs for every single one, but you're going to have 7 outputs. Where is segment B? Segment B is this guy right there. When's it light up? Well, it lights up in 0, 1, 2, 3, 4, 7, 8, and 9. Okay, so the only 2 it doesn't light up in is 5 and 6. Okay, what causes it to light up? A 0, because it's common anode. So when we don't want it to light up, we want to have a 1, 5, 6. All the rest are zeros. Okay, go ahead, put it in the K-map. And again, this is K-map for the seg B. And here's seg B without the don't cares. Go ahead, put those don't cares in there to start off. Where's 5 and 6? Well, if that's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. You can do this too. Oops, you do it right correctly. 10, 11, 12, 13, 14, 15. You can do that. Where's 5 and 6? 1, 1. So what are the groups that I'm going to use? And again, let's try this without the don't cares. 1, 1. Without the don't cares, I can get a 4-term product and another 4-term product. Whereas with the don't cares, use them if it helps me. There you go. Use them if it does help you. There you go. Bigger group. Do I want this one? No, it doesn't help me. Okay, I'm adding an unnecessary product term. Red, so I've got C, not B, A. The blue term is also going to be C and B, not A. Put them all together in our little output file right here, output expressions, segment B, just put it right below segment A, or again, using those don't cares have made smaller product terms for us. This one in red would have had 4 terms. This one in blue would have had 4 terms. I'd much rather use ones with 3 terms. Ones with 3 terms as opposed to the full ones. You have a bunch of examples, C, D, E, F, and G that could potentially work out. And you've got those 2 to 6 detector, for example, 4. And we'll revisit a couple of these things when we do the Unit 5 review. This concludes the combinational logic design using Karnaugh maps.